Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast is going to cover kinetics and solubility. In terms of kinetics, I will cover the general concept of chemical kinetics. I'll talk about rate laws, and that's where I'll spend most of the time in the kinetics section of the podcast is on rate laws. And then I'll get into a little bit on the variables that affect kinetics of a reaction, things like temperature and pressure, different types of solvents, stuff like that. And then I'll get into solubility, again starting with the general concept of solubility, and then I'll get into solubility constant, or a Ksp, or Ksp. And then I'll talk about the common ion effect, and lastly, I'll talk a bit about selective precipitation. And this material is going to show up on one out of the 4 MCAT sections. That is going to be the Chem Phys section. Obviously, this is Gen Chem stuff, so you mostly see it in that section. And this stuff is fairly important. I'd put it somewhere along the lines of like 7 out of 10 on the yield score, if 10 out of 10 was the yield for like amino acids or something that comes up 10 different times on the MCAT. So this is stuff that you'll definitely see. It might not be 10 questions, but you'll definitely get a few questions on kinetics and solubility. And you're most likely to see some kind of calculations. These are typically pretty simple calculations. You just need to be able to remember the equations and remember some of these caveats that come with the equations. And I'll discuss this. And also, I'll bring up some stuff that's good to put on note cards and memorize in terms of solubility on the MCAT. All right, so the first topic I want to talk about in this podcast is reaction kinetics. And so kinetics, in terms of chemistry, deals with understanding the speed or the rate of reaction. And this is in direct contrast to thermodynamics, which looks at equilibrium of a reaction. And thermodynamics essentially is trying to tell you how much of a certain product will form after an unlimited amount of time. If I set, 2 reagents in a flask and I just kind of swirl it around for an infinite amount of time, I'm just sitting there till I'm old doing this, how much of a product will form? On the other hand, kinetics is like, how fast does this reaction take place? And an example I gave from the thermo podcast was this reaction in which diamond turns to graphite. So based on thermodynamics, this is a spontaneous reaction. In other words, diamond turning into this ugly, grayish carbon graphite is a spontaneous reaction, but it doesn't happen in our lifetimes because the kinetics is just so slow. It would take literally thousands of years for the diamond that you wear on your hand to turn into graphite. And so we never really see this reaction go to its full completion. And of course, this could go the opposite direction too, right? I know reactions that are just mere seconds in length. And I'm not putting anybody in the hot seat here, but you know who I'm talking about. And again, this speed or rate of reaction is called chemical kinetics. And under this tree or this umbrella of chemical kinetics, there's what's known as enzyme kinetics, which is just a small branch of it, but very important for the MCAT. And this is discussed at length in my podcast that is the Enzyme Kinetics, Inhibition, and Categorization. I think it's like more than a third of that podcast is just dedicated to enzyme kinetics, which is very important for the MCAT. So if you haven't listened to that and you don't really understand enzyme kinetics, go do that. This is really just going to be reaction kinetics in terms of Gen Chem. All right, the first thing that I want to talk about regarding reaction kinetics is its relation to activation energy and a reaction coordinate, which is just a reaction diagram, essentially. It's got the energy of the products, the energy of the reactants, and then you have this curve that kind of shows the relationship in not only energy, but it does show a little bit about the kinetics of the reaction. So when we look at a reaction coordinate, we see that we have reactants and then we follow the curve, it goes to products. And so we can either have an endothermic or an exothermic reaction in which our products are at lower energy or higher energy than our reactants. In this case, it doesn't matter because I want to talk not about thermo, I want to talk about kinetics. And so in terms of kinetics, what you'll see on the reaction coordinate is this big hump that you go from reactants, you go up this big hump, and then kind of go down to products if you are doing an exothermic reaction. And so this hump that you go over is called the activation energy. And essentially, the bigger the hump, the higher the activation energy, and the slower the kinetics. And so you can kind of think about this as like the reaction has to walk up this hill in order to get down to the products if it's an exothermic reaction. And so the bigger that this activation energy, then the slower this reaction goes because it's going to take it longer to get up that hill. And that's, of course, not what's going on, but it's a good way to kind of think about it. And I'll talk more about theoretically why this is the case, that when you have a higher activation energy, you get slower kinetics. I'll talk about that when I get to the Arrhenius equation. But just for now, just kind of understand that if I raise the activation energy, I'm also slowing the reaction, or I'm making this reaction slower. And so this big hump, or this activation energy, can actually be lowered by what's known as a chemical catalyst. And an enzyme is an example of a catalyst. It's a little bit more specific, more geared towards biological reactions, but in principle, it's a catalyst. And so again, a catalyst lowers the activation energy of a reaction, or it changes the reaction mechanism, resulting in a lower energy transition state, which ends up doing the same thing, and that is making a reaction proceed faster. And so it's kind of easy to think of a biological example, right? We're all familiar with enzymes, but you might be kind of thinking, okay, what about chemicals themselves that are catalysts? Well, what are those? Well, one example is a catalytic converter, which is a part in a vehicle that essentially converts harsh gases that are being emitted by a vehicle into less harsh gases that are then emitted out the vehicle's exhaust. And so the catalytic converter is essentially this big box that exhaust passes through, and the surface of the catalytic converter, the inside surface, is covered with transition metals that are able to catalyze reactions that turn toxic gases into less toxic gases. So take, for example, carbon monoxide, right? We don't want carbon monoxide floating around in our atmosphere. So what happens is this carbon monoxide passes through the catalytic converter and participates in, say, a redox reaction with the transition metal to then become carbon dioxide, which is a lot safer of a molecule. And I'm kind of making up that example. I don't know exactly the reaction going on, but I do know that catalytic converters use metal catalysts in order to convert very toxic gases to less toxic gases. And they do this through a multitude of reactions, one of which is a redox reaction. The overall takeaway message here is that catalysts do not change the thermodynamics of a reaction, i.e. the energy of the products versus the energy of the reactants. Altogether, that's the delta H of reaction. What they do is they lower the activation energy, that hump that you see in the reaction coordinate. They make that hump smaller. Another way to think about this is K, probably very, very anti-catalyst. So just remember that. And lowering the activation energy leads to a quicker or more fast reaction, a higher reaction velocity. The next thing I want to talk about here is called collision theory. And collision theory underlies a lot of the kinetics that I'm going to talk about and underlies a lot of how we believe these reactions take place. And so collision theory states that the reaction rate of a chemical reaction is proportional to the number of collisions between reactant molecules. And further, it says that these collisions must follow three general rules in order to produce a successful reaction. Number one, the reactants must collide with each other. That's what I just said, basically. Number two, the molecules must have sufficient energy in order to initiate the reaction. And this energy is called activation energy, which is that hump in the reaction coordinate that I was talking about. And then lastly, these molecules must collide in the proper orientation. And I think that last piece is a little bit confusing. So I'm going to give you an example that kind of elucidates this concept. So what do I mean by orientation? Well, let's take the example of an SN2 reaction. So in an SN2 reaction, you have a nucleophilic attack that has to happen from the backside of the electrophile. And what this ends up doing is this actually inverts the stereochemistry. And so if we look at collision theory and try to apply collision theory, then we're going to have to say, okay, well, in order for this reaction to occur, I have to have the nucleophile and the electrophile collide at a certain configuration, i.e. the nucleophile has to be behind the electrophile for this reaction to take place. So that's kind of how orientation can play a role in reactions. And of course, there's probably a million other examples, and you could probably think of one off the top of your head, but hopefully that helps you kind of see how this works. So as I continue to introduce these different topics within kinetics, just remember these three principles: that when you have a reaction occur, you number one have to have molecules collide with each other and with enough energy to overcome the activation energy of a reaction and in the proper orientation for that reaction to occur. So a lot has to happen before the reaction can actually occur, and the time that it takes for this to happen is what kinetics deals with. And so in terms of kinetics, the sausage is really made on the MCAT in the category of rate laws. So I'm not sure if I'm using that phrase right, but the highest yield topic within kinetics is definitely going to be rate laws. So you're going to see a lot of determining rate laws, determining rate orders, and stuff along those lines. So that's what I'll get into next. So in general, a rate law describes the rate of reaction in terms of different variables that you know. So it can be a lot of different variables. You can have these really, really complex rate laws that involve fractions and weird exponents and stuff, but you're really only going to see pretty simple stuff on the MCAT. So that's what I'm going to talk about. And typically what you'll see is something along the lines of the rate of reaction, which is also called the reaction velocity, is equal to a constant times the concentration of reactant 1 raised to some power times the concentration of reactant 2 raised to some power times the concentration of reactant 3 raised to some power, and so on. So just to give a quick example, imagine that we have this reaction in which A plus B go on to make C and D. Well, then the rate law would be that the reaction rate is equal to K times the concentration of A raised to some power times the concentration of B raised to some power. And these powers are really what you're going to be interested in finding, because this determines the reaction's order. So again, you have A to some power, and that is the reaction order with respect to reactant A. And then you have B to some power, and that power is the reaction's order with respect to reactant B. And together, if I was to add up those two exponents, that would be the total reaction order. And a lot of the questions that you're going to see about rate laws on the MCAT are going to kind of revolve around finding the reaction order. And so there's two different ways of determining the order of a reaction. And the first of which is using experimental data, which you might remember from Gen Chem. And the second is knowing that the reaction is an elementary reaction and then using the reaction stoichiometry to then fill in the exponents. And those can be kind of mixed up sometimes, and I'll get into what I mean by that. But first, let me talk about how we can determine the rate laws using experimental data. So the experimental data that you'll be given is just going to be a series of experiments in which someone added varying amounts of reactants and then measured the initial reaction rate of some reaction. And I don't know if I mentioned this already, but the units of reaction rate are usually in moles per second or nanomoles per second, some kind of molar concentration divided by seconds. So it's good to know. As I was saying, you'll be given experimental data. This data will be in the form of changing reactants and then looking at reaction rates. And so what you'll be looking for is you'll be looking for two experiments in which only one of the reactants is changing. In other words, you're holding constant all the reactants except for one, and then that lets you kind of determine the effect of changing that one reactant on the overall reaction rate. So it's kind of like a study that says, okay, I'm feeding these people hamburgers. Hamburgers are making these people gain weight. Well, what from the hamburgers is making them gain weight? Is it the bun? Are they eating too many carbs? Is it the meat? Is it too much meat? Is it the cheese? Is it from dairy? Well, if you're just feeding them burgers, you're never ever going to be able to determine what exactly is making these people gain weight. You have to isolate one of the variables. So you got to feed either just meat, feed somebody just the bun, or feed somebody just the cheese in order to determine the effect of that variable. So in the same way, you're picking two experiments that you only change a single variable, so then you can determine that variable's effect on the overall reaction rate. And so given experimental data, this is what I usually do in order to determine the overall reaction rate and the reaction rates for each of the reactants. First thing I do, as I said a little bit earlier, was I look for 2 experiments in which I'm only changing a single reactant concentration. Once I find these 2 experiments, I compare their reaction rates and I compare the concentration of reactant that is changing. And I write down each of these numbers. So say, for instance, the concentration of the reactant doubled. Well, then I write down 2 and then say that the reaction rate went up by 8 times. Then I write down 8. And now I use pretty simple mathematics. I say that 2 to the n is equal to 8. And I solve for n, and that is my order, which in this case is 3. And essentially what this 2 to the n equal to 8 expression is saying is, by what factor does the reaction rate change if I change the concentration of reactant X? So you're just looking at what happens to the reactant rate if I change the input concentration of a reactant. And so once I do this for one reactant, I'll go ahead and do it for the next reactant and the next reactant until I have all the orders for each of the reactants. And then boom, now you have the rate law. You know now that you have A to the third times B to the second, or B to the first, whatever the order of reactant B is. And then what you can do is you can add up these individual orders for each of the reactants to determine the overall reaction order. So just remember, the overall reaction order is simply the sum of the individual reactant orders. Okay, so that is mathematically how you determine the overall rate law or determine the order of a reaction. What about the other way I was talking about? Well, the other way to determine the rate law for a reaction and determine the reaction order is to get it from the stoichiometry. But this has a huge caveat. You can only do this when the reaction is elementary. And what do I mean by elementary? Well, elementary simply means that the reaction is a single-step reaction, which, if you think about a lot of these biological reactions, they're not really one step. Take, for instance, the reaction that converts glucose to 2 molecules of pyruvate. Is that reaction elementary? Well, if you answered yes, then you are probably not ready for the MCAT, or you're maybe retaking it now. But a single-step elementary reaction would be something like a molecule of oxygen and a molecule of oxygen react together to form O2. Something like that. Glucose, on the other hand, goes through a bunch of different steps in order to make pyruvate. It goes through all these steps of glycolysis in order to make pyruvate. You release 2 ATP, you require some NADH, or I guess you produce NADH. But anyways, the point I'm trying to make here is that unless you are very specifically told, this reaction that you're given is an elementary reaction, do not use the way I'm about to tell you to determine the rate law for a reaction. Instead, you're going to have to use experimental data that you've been given in order to determine the rate law. So never just skip ahead to this step unless the passage says this reaction is If a reaction is indeed elementary, my dear Watson, then all you have to do is you use the stoichiometric coefficients from that reaction and just plug them in to the reaction order for each reactant. So let me give you an example. Let's say that you're given the equation that 2 O2s react with 1 CO2 to form CO4. And I'm just making that up, but just pretend that that's the case. Well, I know that my rate law is going to be that the rate is equal to some constant K times the concentration of O2 raised to some power times the concentration of CO2 raised to some power. All I got to do, since I know the reaction is elementary, is I go back to the original reaction, and I know that the stoichiometric coefficient for O2 is 2. So I just say K times O2 squared. And then I look at the stoichiometric coefficient for CO2. I see it's a 1. And so I just leave CO2 as it is, right? Anything to the power of 1 is just itself. And in the end, the rate law then becomes that the rate of this reaction is equal to K times the concentration of O2 squared times the concentration of CO2. So again, all I did is I took these stoichiometric coefficients and I plugged each of those into the exponent for each of the reactants. And I've honestly seen the MCAT do this either way. So they might give you experimental data and you have to solve then for the reaction order using the experimental data, or maybe they don't give you experimental data, but somewhere in the passage it says this elementary reaction, blah, 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 and then you'll get asked about the rate law. So the MCAT can ask you in a few different ways. Just understand that if you're not explicitly told it's an elementary reaction, don't just assume the stoichiometry determines the rate law. That is a huge mistake that students make, is they'll say, okay, I have the stoichiometric coefficients for the reaction, I'm just going to plug these into the rate law. Well, that's bullshit. That's not how that works. And so what you got to do is you got to use experimental data then that you're given, hopefully, to be able to solve for that rate law instead of just taking the easy way out with the coefficients. All right, the last thing I want to talk about in terms of kinetics is what's called the Arrhenius equation. And so you may have noticed that I kind of didn't talk much about this reaction rate constant K that shows up in the rate law. Well, now I'm going to focus on that and talk to you a little bit about that reaction rate constant. And I would just want to preface this by saying that you can actually determine this rate constant using experimental data. So let's say that you're given a set of experimental data, you have to solve for the reaction order, you do that and you determine the whole rate law. Now it says determine K. Well, all you're going to do then is pick one of the experiments and plug in all the information. You'll plug in the concentration of your reactants, you'll plug in your rate, and then from there you can solve for K because that's the only unknown variable. So you could be given a problem like that. Just don't forget that. That should be an easy give me because you're just plugging in numbers. The Arrhenius equation, on the other hand, is more of a theoretical equation, or that's how I kind of see it on the MCAT. It's more of, if I change this variable, what's going to happen to the reaction rate? What if I change the pressure? What if I change the temperature? I think that's more of how I would use that on the MCAT. And so the Arrhenius equation is that K, which is the reaction rate constant, is equal to A times E, which is E in terms of the natural log base, to the power of, in parentheses, negative activation energy, or EA, divided by R times T. So it's a bunch of variables. Let me kind of break that down for you. So this is saying that the reaction constant K is equal to some pre-exponential factor, which is just a constant for each chemical reaction, times E, which again is this natural log base, to the power of negative activation energy divided by the gas constant times temperature. Now, obviously, this is kind of a convoluted thing to try to explain over words. So if you don't know what I mean, go look up a picture of this equation or something like that. Just Google Arrhenius equation real quick, and then you'll be like, oh, yeah, that makes sense. And so in order to use this equation, you first have to understand that the reaction rate of a reaction is proportional to this rate constant. All right, so think back to the reaction rate law, in which you have rate is equal to K times concentration of reactant to some power. Right, so that's proportional. So as K increases, the reaction rate increases. That's our starting point, is saying that the constant K is proportional to reaction rate. And so once I know that, then I can take a look at each of these different variables in the Arrhenius equation and see what each of them does to the reaction rate. So first we'll look at A. And what I have to say here is that I wouldn't worry too much about A. This has to do with how hard it is for molecules to collide in certain conformations to react. Like basically saying, do they have to collide in a very, very specific manner in order to react? Or does it not matter the conformation they collide in order to react? And so if you have a big A, then that means that it's really easy for these molecules to collide. They don't have to be in a super specific conformation, and therefore you have a high reaction rate. Now, if this is lower, then that means that these have to collide in kind of a more specific manner, and therefore the reaction rate's a little lower because of that specific collision manner. And then activation energy is in the numerator of the exponent, and it's also negative. And so because of this, the activation energy is inversely proportional to the reaction rate constant. In other words, as the activation energy increases, the K constant decreases. And that makes sense, right? If you have a high activation energy, you're probably going to have a lower reaction rate. And then the last variable that you want to look at is temperature. And I think this is probably the most important to understand. Also pretty self-explanatory, right? You think hotter temperature, a faster reaction, and your intuition is correct. So if you look at the T, it's in the denominator of the exponent. And so therefore it is directly proportional to the reaction rate constant K. So if I increase the temperature, then I'm increasing the reaction rate constant K, and I'm getting a faster reaction. And then if it gets cooler, then I'm decreasing K, and now I'm getting a slower reaction. And I can actually do this analysis for pressure as well. All I got to do is assume that I have an ideal gas. Note that this is just for a gas, right? Changing the pressure of a solid or a liquid doesn't really do much. But say I have a gas, I can use PV equal to nRT and then solve for T and basically plug that expression into the Arrhenius equation and then see what pressure does to a gas phase reaction. And long story short, it does the same thing as temperature, and therefore the pressure and the reaction rate constant K are going to be directly proportional. So as I increase the pressure of a gas reaction, it is going to result in an increased reaction rate constant K, which is going to result in an increased reaction rate. And so this makes sense, right? Let's say I have a gas and I take that gas and I pressurize it into a smaller volume. Well, now you're going to get more collisions and you're going to get a higher reaction rate. So in summary, there are two kind of main takeaways from kinetics for the MCAT. The first is being able to determine rate laws and reaction order. And so you'll either be given some kind of experimental data and be asked to solve for these things, or you might be told that the reaction that you're looking at is elementary, which makes your life a lot easier. The second thing you should know how to do is know how to work with the Arrhenius equation. So imagine the MCAT gives you that you change the temperature of some reaction by 4 times. What's going to happen to the reaction rate? So have that equation memorized and be able to use it then to solve these proportionality problems.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's Mcat Tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
All right, the next thing that I want to talk about in this podcast is solubility. And so I'm going to talk about a few different things in terms of solubility. I'll give you the definition. I'll talk about Ksp. And then similarly to kinetics, I'll talk about the effect of temperature, pressure, and some other things you'll see. And I'll throw in there the common ion effect, which is something I've definitely seen on the MCAT. So solubility is a chemical property that describes the ability of some given substance, which is called a solute, to dissolve within a solvent, which is usually a liquid, and the solute is usually a solid, but there's other forms, and I'll talk about that. And so it's measured in terms of the maximum amount of solute dissolved in a solvent at equilibrium. And a solute's solubility is very dependent on the solvent that you're using. So say, for example, I take 200 grams of sugar and I add that to 100 milliliters of water, and it all dissolves after like 15 minutes of shaking it in whatever container I have. Well, now I take 100 grams of sugar and I try to dissolve it in 100 milliliters of pure ethanol. It's not at all going to work. I mean, maybe you dissolve like a gram or two of the 200 grams, but only a very, very, very small fraction of that is going to dissolve in ethanol. So the solubility of a certain substance is very dependent upon which solvent you're using. And I should further mention that polar solutes like to dissolve within polar solvents. And on the other hand, nonpolar solutes like to dissolve within nonpolar solvents. Take, for example, fat-soluble vitamins. So these are vitamins that dissolve in fat. And so typically, if you are supplementing these vitamins, you try to take them with a meal or take them with milk or something that's got a little bit of fat in them so that your body can more readily absorb those fat-soluble vitamins. And so polar solvents are able to dissolve polar solutes through interactions with these solutes. So polar molecules in general have a negative side to the molecule and a positive side to the molecule. Therefore, they have a polarity. And in terms of water, you have a partially negative oxygen and two partially positive hydrogens that are on opposite ends of this molecule, rendering it polar. And what happens is that this polar water is then able to interact with whatever solute is in solution. Let's take NaCl, sodium chloride, which is just table salt. The water is essentially able to kind of surround each of these individual ions that make up sodium chloride, which is sodium and chloride, and pull them apart from each other. So it's kind of able to segregate them away from each other using its polarity as kind of like this shield to surround each of these individual ions. In terms of sugar, take the example that I was talking about earlier where you're dissolving a bunch of sugar in water. Well, sugar doesn't really form ions, so you're not surrounding these ions. Instead, the water acts to kind of break these weak intermolecular forces between sugar molecules in order to isolate these individual sugar molecules that are then in solution and dissolves these kind of bigger clumps or crystals of sugar. And again, this is all because of the polarity of water. Now, on the other hand, if you have some kind of nonpolar solvent, like say hexanes, and you try to dump some sodium chloride into there, the hexanes are not going to be able to interact with the sodium chloride and therefore not able to pull these ions apart and dissolve the sodium chloride. And so you have really low solubility in a nonpolar solvent because of its lack of charge. And so big takeaway really is that nonpolar things dissolve in nonpolar solvents, polar things dissolve in polar solvents. Pretty simple. The next thing I want to talk about is Ksp, or solubility product, which is going to be the equilibrium expression for a dissolution reaction. And what I mean by dissolution reaction is just some solid dissolving into its component ions. So again, back to the sodium chloride example, you have solid sodium chloride producing sodium cations and chloride anions. So as with all equilibrium expressions, Ksp is simply equal to the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. This is the same thing for Ka, Kb, all those different equilibrium expressions. The trick here, though, is that we can get rid of the sole reactant. Because what's the reactant in this case? Well, it's going to just be some solid. Well, the equilibrium expressions do not contain pure solids. So essentially, we can just X out the denominator of this expression, and we simply get that the Ksp is equal to the concentrations of the products raised to their stoichiometric coefficients. So that's pretty simple. And these products are going to be ions typically. I'm not sure exactly how this would look for sugar. I don't think you really need to know that. Really just know that the Ksp is equal to the products of a dissolution reaction raised to their stoichiometric coefficients and does not include the reactant because it is a pure solid. And that goes for all equilibrium expressions ever. Pure solids, pure liquids, they're just way better than everything else, I guess. They just don't even want to join the equilibrium expression party. They don't even come. So just keep that in mind as you're working through chemistry problems on the MCAT. In terms of equilibrium expressions, pure solids and pure liquids, they never show up. And in terms of questions on the MCAT, there's a few different ways that they like to ask about solubility product or Ksp. The first is that they may ask you to calculate the solubility of some solute given a Ksp, or they might ask you to do the reverse calculation where you are asked to calculate the Ksp given solubility. And then third, they may ask you to compare the solubilities of a few different solutes. So let me quickly go over how to do these calculations, starting with the first example, and that is calculating the solubility of some solute given the Ksp. And these problems are pretty simple. They can get a little bit tricky when you start having to consider stoichiometry. But essentially what you do is you first set up the solubility product expression, or the Ksp expression. And let's just do the example of sodium carbonate. So the MCAT says something like, calculate the solubility of sodium carbonate given this Ksp. And so the first thing you're going to have to know how to do is you're going to have to know how many of the sodium ions go with the carbonate ion. And so that goes back to just memorizing these common ion charges. So I definitely recommend you do that and put together some of those very common ions onto note cards and memorize them. And I think I'm going to do a bonus episode where I just basically go through all these different common ions to know, sort of like a verbal note card. All right, so back to step 1 of setting up these problems. So again, you got to be able to set up this Ksp expression, and to do that, you need to know the stoichiometry of this dissolution reaction. So sodium carbonate, for example, is Na2CO3. And you could be given the formula for this on the MCAT, but most likely it's just going to say sodium carbonate, and then you have to pull Na2CO3 from your memory. And so sodium carbonate breaks down into 2 sodium ions and 1 carbonate ion. And so then what I do is I go through and make this expression, and the expression then is going to be equal to the products to the powers of their stoichiometric coefficients. So this becomes Ksp is equal to the concentration of sodium squared times the concentration of carbonate, or CO3. And at this point, you could pull out an ice table and go through the ice table and then plug in these different variables and solve for the solubility. But for me, it's easier just to look at the number of ions that are going to be produced and then use the variable x, plug that into the Ksp expression, and then solve for the solubility, which is going to be that unknown variable. So this is how I do that. I look at the stoichiometry of the reaction and say to myself, okay, so I know for each molecule of CO3 that I produce, I'm producing 2 molecules of sodium. And so therefore, if I produce X molecules of CO3 after dissolution, then I must produce 2X molecules of sodium. So I make 1 molecule of carbonate, 2 molecules of sodium per mole of sodium carbonate that is dissolved. So then for my concentration of sodium, I plug in 2x into my Ksp expression, and then I just plug in x for my concentration of carbonate, and then I just solve for x. And again, you're going to have 2x squared times x. And so you got to square the 2x, and that is going to be 4x squared. I see a lot of students mess up there. You got to square the whole expression. 2x times 2x is 4x squared. And then 4x squared times x is going to be 4x cubed. And so then once I have this expression simplified, I have 4x cubed is equal to Ksp, and I'm given the Ksp, I can just divide by 4 and then take the cubed root. So I'm just solving for x. I'm just doing simple algebra, and that'll give me my solubility. And so this brings me to another point or common error that I see on these type of problems. So that x that you just solved for is the molar solubility of sodium carbonate. And so that is also going to be the concentration of carbonate that is produced once this sodium carbonate is dissolved, because the molar ratio from the solid to the carbonate is the same, right? It's just 1-to-1. However, if they ask you for the concentration of sodium in the solution after the sodium carbonate is dissolved, you have to remember that this concentration is going to be equal to 2 times that x that you just solved for. So it's 2 times the molar solubility of the solid. In other words, it is just that 2 times x. So this is something you always got to remember when you're working through these problems, is stoichiometry matters. If this stuff is kind of difficult for you, or this is a hard concept, go do some practice problems. That's always better than just listening to me talk about it. But big key here is do not forget about the stoichiometry when it comes to these Ksp problems. Another quick note, there's a few different things the MCAT might ask you in terms of the solubility. So they could just ask you, what is the solubility of sodium carbonate? And in that case, that is just this x. They could also ask you, what is the concentration of carbonate? That's that x. Or they could ask you, what is the concentration of sodium? And as I alluded to, you have to use a stoichiometry there. That's going to be 2x. All right, so the second type of problem you might see regarding this Ksp is calculating the Ksp given solubility. So this is pretty easy. Basically, it's the opposite calculation of what I just did. In this case, you will be given that X or that solubility, and then you'll have to calculate the Ksp. So if you go back to the expression that I derived earlier, you have Ksp is equal to 4x cubed. So in this case, you'll be given the solubility, which is the X. So all you got to do is plug that solubility into the X, cube that X, multiply it by 4, and then you will calculate your Ksp. And again, I think the most tricky or hardest part of this is being able to set up that Ksp expression. Practice, practice, practice if that's hard. The last and still very important type of question they may ask you regarding Ksp is to compare the solubility of different solutes given their Ksps. So this comparison comes down to two different factors. The first being their relative Ksp values, and the second being the number of ions that they produce. So when I'm comparing the solubility of a bunch of different compounds, the first thing I want to look at is Ksp. And so the greater the Ksp, the more soluble a compound is. And so that's where I kind of start. I look through their Ksps and I say, okay, these are the relative values of their solubility. The next thing I look at is the number of ions they produce. You can go through and do the math if you want, if you're a narc, and you will find out that the more number of ions that a certain compound produces, the higher its solubility will be. So the first check I go through is I look at the Ksps, and then I'll look and see, okay, how many ions are being produced. If they all produce the same number of ions, then I can just go off Ksp, and I'll pick the one with the highest Ksp if I'm looking for the one with the highest solubility. However, if that's not the case and these produce different numbers of ions, then I have to factor that in. And so sometimes this will require you to do a calculation. You can do this again by setting up the solubility expression and solving for that X, which determines the solubility. But sometimes you can kind of logic your way through it. So let's say that you're given 4 different compounds and asked to determine which one has the high solubility. Well, let's say 2 out of those 4 compounds have really high Ksps and the other 2 have really low. Well, then I'm just going to pick those 2 because I know that even if one of the compounds with a really low Ksp produces multiple ions, it's still not going to have as high solubility as these 2 with the really high Ksps. So I take these 2 and I look at them, and they have basically the same Ksp. So the next thing I look at is how many ions they produce, and I see that one of them, which is NaCl, produces 2 ions. The other one is going to be calcium hydroxide, which is CaOH2. And so I know this produces 3 total ions. So then I'm going to say, okay, well, the one that produces 3 ions is going to have the highest solubility, and boom, I just found my answer without having to do any algebra, which is sweet. So in summary, I use both the number of ions produced by a compound as well as its Ksp in order to determine its relative solubility compared to some other different compounds. And really the order, and I said it earlier that I said that I first looked at Ksp, then number of ions. Really you should look at number of ions first in order to determine if you can then compare the Ksps equally. Like you can equally weight all the Ksps. If not, it gets a little more complicated, and as I said, sometimes you can kind of logic your way through it. Other times you'll have to actually run the calculations. Maybe you can get it narrowed down to between 2, but then you're like, I don't know how close the Ksps are together. What effect does the number of ions have? How much does this going to change the solubility? And then you'll have to run that calculation until you can really see which one has the higher or lower or whatever solubility you're looking for. All right, the next thing that I want to talk about in terms of solubility is the common ion effect. And the common ion effect says that the solubility of an ionic compound is decreased by the addition to the solution of another ionic compound that contains one of the ions involved in the solution equilibrium. So let me give you a quick example of how this works. So say that I want to make my water taste better, so I add potassium chloride or KCl to it. And so when I add this, it's going to all dissolve and I'm going to get a bunch of potassium ions and a bunch of chloride ions floating around. Yum. And then I realize that I also forgot to add the table salt to my water because I need it to be a little more salty. So I add NaCl, and again, the NaCl breaks down into its component ions, which is sodium and chloride. And what happens is that this decreases the solubility of each of these individual salts. So if I had sodium chloride alone in its own glass and potassium chloride alone in its own glass, they'd have higher solubilities than if each of these were combined into the same solution. And that's because they both contain a common ion, which is chloride. And there's not really any calculations per se that you would see involving the common ion effect. Just have an understanding that when you're adding two different salts into the same solution, that their solubilities will decrease if they contain a common ion. So basically just understand the concept in general. Another effect that you should know that's sort of similar to the common ion effect is what's known as selective precipitation. And hopefully this throws you back to Gen Chem 2 lab where you had to determine what was it, a metal? What transition metal was in some vial or some stupid lab. But essentially what selective precipitation is that you can precipitate a particular salt in a solution by the addition of another salt. And so essentially this works by this principle. So many salts are soluble and many salts are insoluble. And unlike two wrongs, two soluble salts can actually produce an insoluble salt. So say, for example, that I have sodium carbonate, which is soluble, and I have copper 2 fluoride, which is also soluble. And so I add these both to water, and what happens is that I have all these ions floating around now. I have sodiums, I have carbonate ions, I have copper 2 plus ions, I have fluoride ions, and they're all floating around until the copper ions bump into some of the carbonate ions, and boom, they form a very insoluble solid known as copper carbonate. And so eventually you get enough of this copper carbonate solid forming until you form big clumps of it and it precipitates out of the solution. And I'm kind of just making up that example. I'm not even sure if any of these compounds are soluble or insoluble, but the principle still holds. And so what you really want to understand here about selective precipitation is that you can add two very soluble compounds together in the same solution, and if any of these ions are able to form an insoluble solid, they're going to do that, and that solid is sure as hell going to form some kind of solid precipitate that is going to crash out of solution. The very last bit I want to throw in here is a little bit on solubility of gases. So it's important to understand that gases can be dissolved in liquids. Think of carbonated beverages, for instance, right? You can have carbon dioxide that is dissolved in water to make seltzer water. And what's really interesting to me is a lot of these new drinks that have dissolved nitrogen. So you can see this in beer, you can see it in coffee, and I think it's called nitro brew or something like that. But essentially what happens when carbon dioxide is dissolved in water is that it reacts with water to form carbonic acid, which gives a little bit of an acidic flavor to whatever beverage you have it in. And this is kind of why when you drink seltzer, it tastes a little bit acidic. And so if you add that to coffee or to beer, it gives it kind of a weird, shitty taste. It doesn't taste good. So what happens is if you take nitrogen gas instead and dissolve nitrogen in either coffee or beer, it doesn't react with water in that beverage, and then it doesn't give it that weird, acidic taste. And so it gives it a nice, smooth taste, which is why you dissolve nitrogen in those drinks instead of carbon dioxide. So interesting aside. But anyways, you can dissolve gases into liquids, and this follows what's known as Henry's law. And Henry's law states that at constant temperature, the amount of a given gas that dissolves in any type of liquid is directly proportional to the partial pressure of that gas in equilibrium with the liquid. In other words, the solubility of a gas directly above a liquid is proportional to the partial pressure of that gas. And in terms of an equation, Henry's law is usually stated as C is equal to K times P, where C is solubility of a gas, K is some constant, and P is the partial pressure of that gas. And just note that Henry's law is only accurate for ideal gases that are of very dilute concentration. So imagine you're being asked about carbon dioxide in air. Well, carbon dioxide is 0.04% of air, so you can apply Henry's law to carbon dioxide in the air because it is at a very low concentration. And so really the takeaway here is that number one, gases can dissolve in liquids, and number two, the relation between pressure of a gas and solubility are directly proportional, meaning that if I increase the pressure of some gas above a liquid, then it is going to increase the solubility of that gas into whatever liquid it's above. And so you can use pressure then to drive gas into a liquid essentially. And that's what you're doing when you are applying pressure to some kind of carbonated beverage to carbonate it, right? You're forcing that gas into the liquid using pressure. So pressure increases the solubility of a gas. All right, so that does it for the Kinetics and Solubility podcast. Keep an eye out for a bonus episode I'm going to release here pretty soon, I think, that goes over the common ions to know as well as the solubility rules. And if anyone has just taken the MCAT and they're kind of pondering over whether to retake it or not, go listen to the interview I did with Sahil Mehta and Ken Tao, who are both very smart, long-term tutors. One of them is a physician himself. And I think we had a really good conversation about when and how to retake the MCAT. As always, thank you for listening. If you like this podcast, please go give us a review on iTunes. It helps us reach more people, helps us in the ratings. Thanks, and hope you listen to the next one.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school, check out medschoolcoach.com for the experts.